between the products and the reactants. So does everyone get that if you have to increase Q, the reaction has to go to the right? Is that cool? Yeah? Okay. So that's B. And then C, number 7, exam 2, is what is the delta G at equilibrium for the reaction above? 0. That one's easy. Remember, if there's not a little 0 above that delta G, it's not standard conditions. Exam 2 was hard. I'll fess up to that. You know, that's why a lot of you guys are sitting here. So, but like I said, the final will be good for you. It'll help you learn. Okay, that was number 7. Yeah.
You said you can use all 3 of our sheets in this?
No problem. Yep. And your periodic table.
If we choose to, can we make a new one?
You can make a new one if you'd like to. Yeah. Yeah.
Would some question like number 3 on exam 2 be acceptable for the final?
You'll have to give it to me.
If it is, then we need to go over it.
Or 6.
3 or 6. Okay. 3 is a bomb calorimeter containing 100 grams of water. Yeah, so I think these are both fair. Now I might not ask you all these details, but I might ask you, you know, if you light off a reaction in water, is the temperature going to go up 1 degree or 20 degrees? You know, so you have some feel for what's going to happen. Or is the temperature going to go down? You know, so here's a good question. If you have, say you put an exothermic reaction, so first we need to know what a calorimeter is. So a calorimeter has some sort of reaction chamber, right? Then it's usually got some sort of water, and we're going to measure the temperature of the water. And the temperature change of the water tells us how much heat is released from that reaction, right? So if I put an exothermic reaction in this box, is the temperature of the water going to go up or down?
In exothermic, you said?
Exothermic.
Up.
Up. Okay, if I put an endothermic reaction in that box, is the temperature going to go up or down? Down. Good. Remember, that's important. Why does the temperature go up? So if I put an exothermic reaction in this box, why does the temperature of the water go up?
Because energy is released, so energy usually is heat, and heat makes the water temperature go up.
Yeah, so Q is going to go from the reaction into the water, right? So heat is going to go into the water. How do we compute the amount of heat that goes into the water? Q equals mCp delta T. What does that mean? Mass? So I need to know how much water is in here. Cp is what for water? 4.184, like that? What is it? Joules per gram per K? Or per C? And delta T is T final minus T initial, or T initial minus T final. It depends what's happening. But this allows me to figure out how much heat is released from this thing. Okay. Oh, I know. Okay, I know why this one was tricky. All right. So this is the reaction. What type of reaction is this? Combustion, right? We're combining oxygen with something. So you have a delta H for this reaction is 1299.6 kilojoules. What does that mean? That 1299.6 kilojoules. the enthalpy, so this is the number of kilojoules, or the number of joules, that's given off from this reaction when I combust 1 mole of acetylene. Okay? So if I have 1 mole, I get 12,999.6 kilojoules. If I've got 2 moles of C2H2, what do I get? Twice that. 2 times 12,999.6 kilojoules. Okay? Yeah?
Why does that mean that it's kilojoules per mole of C2H2?
So this is written, remember, when I write something like this, without any units, it means for this exact reaction. So if I wrote kilojoules per mole, I have to tell you per mole of what? But this is written for this reaction, so I need to look at the stoichiometry. So for 5/2 of oxygen combined, or 5/2 of oxygen reacted, I need to use that much enthalpy. Okay, so how many moles of acetylene do I have in this problem? I have 0.1 grams, let's see, divided by, acetylene is 26 grams per mole. And so this is the number of moles that I actually have of the acetylene, whatever 0.1 divided by 26 is. So that gives me moles of C2H2, and I multiply it by 12,996 kilojoules. Then I take that number of joules and go right back to here and try and figure out what my final temperature is. And so I have 100 grams of water. I know what this number is, and I have to figure out what the final temperature is. And so I think the hard part about problem number 3 was how many moles of acetylene do I have, and how much heat is that going to give off? That's the key to that problem. And so, you know, I might not make you go through, or I probably won't make you go through the whole thing on the final, but I could certainly ask you the parts. Say I gave you this reaction and I said, how much heat is released when I burn 6 moles of acetylene? 6 times this, you know. Yeah?
So you just solved for Q, what did you just solve for right there? What was the,
Oh, yeah, so Q of the reaction is moles of C2H2 times 12,999.6 kilojoules.
okay, so all that calculation right there is to find your Q value.
That's to find the Q of the reaction.
Okay.
Then I compare that to the Q of the water, right? Because the Q of the water is mCp delta T.
Okay.
And Q of the water has to equal Q of the reaction because they're going to exchange heat, right?
Right, okay.
Remember, all the heat that's generated in this in the calorimeter has to go into the water. So we can equate those two heat flows.
So the number you find is the Q you plug into that equation now?
Exactly.
Okay.
Or I could ask you something about the water, right? Say you have 1 mole of acetylene and you put it in a calorimeter with 10 grams of water versus a calorimeter with 100 grams of water. What's the delta T going to be higher in? The one with 10 grams of water or the one with 100 grams of water? Higher delta T. Yeah.
10 grams?
Yeah, why?
Because there's less amount, so the heat goes to a smaller mass.
Yeah, so you just have to think about, you know, you can either use this equation, 10 versus 100, so say this number is 3,000, right? And I've got 10 versus 100 here, what's my delta T going to do? Because Cp is constant. So you can either say, okay, I've got a little water, and I'm going to dump a bunch of heat into it, how much does the temperature go up versus I've got a lot of water. I'm going to put the same amount of heat into it. The water temperature only goes up a little bit. Or you can use the equation to try and figure out what you've got. So I'd probably only ask you one half or the other, right? Okay, 6. 6 was the iron problem, I assume? Yep. Piece of iron rod is heated in a Bunsen burner and then plunged into a bomb calorimeter containing 1,000 grams of water. Okay. So remember to think about the physical process that's happening. That's how you get a handle on some of these problems. Iron rod is heated and plunged into water. Q, iron, equals Q, water. Start with that. The original temperature of the water was 20 C. And the final temperature of the water is 32.8. A 1,000 grams of water. What was the original temperature of the iron rod? Okay, so we know 400 grams of iron. We know that the heat capacity of iron is 0.45 joules per gram per degree Celsius. Let's see, what's the final temperature of the iron?
Whatever the water is.
Same temperature as the water, right? So at T final iron is 32.8. What's the initial temperature of the iron? That's what we're trying to solve for, right? Can we solve for it using this equation? Yeah. One unknown. We know all of these other things.